Hello everyone, welcome to the HCIA WLAN Huawei Certified Wireless LAN Engineer online course. This section mainly introduces the concept of wireless communication, key WLAN technologies, the 802.11 standard, and Wi-Fi 6 technology, among others. The main focus actually is on the working mechanism of WLAN. What exactly is the working mechanism of a wireless network that allows a normal WLAN network to continue operating? That's the focus of this section. It could be said it's the focus throughout the HCIA WLAN course. If you can master this course, it indicates you have an introductory understanding of WLAN technology and can basically understand how Wi-Fi technology operates. After completing this course, you will be able to explain the basic concepts of wireless communication, differentiate the 802.11 protocols, list out Wi-Fi generations, and describe the highlights of Wi-Fi 6 and WLAN key technologies. We'll begin with the first subsection on the basic concepts of wireless communication. First off, it's radio waves. Everyone must understand how signals like Wi-Fi, AP, or 3G, 4G, and 5G are transmitted. They are all transmitted via electromagnetic waves. Radio waves are a type of electromagnetic wave, and we're mainly concerned here with how they are transmitted. Radio waves are a form of wave, but how are they transmitted? This involves various different concepts. First is wavelength. What is the wavelength of a wave? Does it have a fixed value? If not fixed, how is wavelength defined? The second is period. What is the concept of a period? Speaking of period, we have another term called frequency, which everyone is clear about. Different applications have specific frequency requirements. For instance, in WLAN, the rule starts from the 2.4 GHz spectrum, which is available for free use. Then, how are wavelength and period defined? Another term is amplitude. What is amplitude? Simply put, is the wave smooth or steep, right? This is radio waves. We use various technologies to alter the information or parameters within the electromagnetic waves to achieve the goal of transmitting data wirelessly. We'll look later at the specific methods by which radio waves can carry data. First, let's look at the frequency and wavelength of radio waves. Frequency, high frequency, and low frequency, I believe everyone can understand easily. High frequency, for example, means looking at how many waves can pass in 1 second. If more are transmitted, like in the left image, that's high frequency. If fewer, like in the right image, that's low frequency. That is, the number of waves or the occurrences that can be completed within a unit of time is called frequency. The second is wavelength, and we have a simple formula for this. C equals L multiplied by F, where C is the speed of light, a constant. The speed of light cannot change, right? So the longer the wavelength, the smaller the frequency, right? If the frequency increases, does the wavelength decrease? That is, these two are inversely related. In our current 5G technology, there's a concept called millimeter waves. If the wavelength reaches millimeter levels, then the frequency might correspondingly decrease. What unit is used to express frequency? Frequency is measured in hertz, which is important to note. For example, 2.4 gigahertz, where G stands for 1,000, everyone should be clear on that. Now, let's look at some common frequencies and frequency bands. Firstly, gamma rays have a very high frequency, right? What about lower frequencies? There are radio waves, which we commonly use, and they are quite low. There are also microwaves, infrared, ultraviolet, etc., which all have certain frequencies. Keep in mind, the electromagnetic waves used in WLAN are what we call radio waves. Let's specifically look at the different frequency spectra. Here, we mainly discuss radio waves. WLAN uses the 5 GHz and 2.4 GHz frequency bands. We categorize them as ultra-high frequency and extremely high frequency. Other frequency bands, like very high frequency, and high frequency, have different applications. For instance, high frequency might be used for civilian radios, while very high frequency is used for FM broadcasting. We only focus on the application scenarios of radio waves, namely the 2.4 GHz and 5 GHz frequency bands. It's important to understand that all these bands refer to a range of frequencies. It's not that ultra-high frequency is a specific frequency. Within this frequency range, I categorize it as ultra-high frequency. Within that range, I categorize it as extremely high frequency. Wi-Fi technology uses the 2.4 GHz frequency band. Its frequency range extends from 2.4 GHz to 2.4835 GHz. This place needs precision to 4 decimal places. Because later we will deal with channel division issues, we will focus on how the frequency range is used. The second is the 5 GHz frequency band. The 5 GHz band is divided into 2 non-contiguous segments. The first segment ranges from 5.15 GHz to 5.35 GHz. The second segment ranges from 5.725 GHz to 5.85 GHz. These 2 bands belong to the Industrial, Scientific, and Medical ISM band. The ISM band does not require license or fees as long as certain transmission power limits are followed. This transmission power is generally less than 1 watt. Without causing interference to other bands, let's continue further. We have a new concept here, which is phase. Phase is a relative number language, describing the relationship between 2 waves of the same frequency. To measure phase, the wavelength is divided into 360 parts, each called 1 degree. We take 0 degrees as the start time for wave propagation. If one wave starts at 0 degrees and another at 90 degrees, they are said to be 90 degrees out of phase. Waves of the same frequency starting at different times can significantly affect the transmission of electromagnetic waves. This needs attention because they all propagate through air and are all forms of energy. If 2 radio signals of the same frequency propagate at the same time and in phase, because the received frequency is the same and the signal phase is the same, then the signals will strengthen each other. For example, if originally there was just one A and now 2 signals are superimposed, it becomes 2A. This is called phase enhancement. There's also signal weakening. If one signal is like this and another is opposite, offset by 180 degrees, then it effectively weakens that signal. In device development, corresponding technologies must be used to avoid signal weakening due to phase issues. These are some of the basic concepts: wavelength, frequency, phase, and amplitude. Next, let's look at how the process of wireless communication works. First, during the transmission of the signal from one end to the other, the signal source is our sending device, and the signal destination is our receiving device. For example, if I want to send a word "hello world," computers are binary. They don't understand your hello world, so we need certain measures to convert it. We need a source encoding to transform it into a digital signal. First into a digital signal, then through channel coding and modulation, converted into radio waves to be transmitted, it is sent through the channel to our receiving device. What is a channel? We mentioned frequency earlier, like 2.4 GHz. This frequency range is quite large. Various frequency signals can go through it, like a road, say 20 meters wide. If you don't plan it, everyone will just wander, and the efficiency will be very low, so we need to divide it into lanes. Each person just stays in their own lane and won't stray into others. The channel is the same. For example, I number them 1, 2, 3, 4, 5, 6, 7. You can only walk in channel 1. This is now the concept of a channel. We divide the frequency into different channels. Through the channel, the signal is sent to the receiving device. In this process, there are no pipelines in wireless networks, nor any network cable ports. Therefore, in wireless, the interface for receiving signals is called the air interface, which is invisible. Then I decode the information you transmitted. After demodulating and decoding, it is then sent to our receiving device. This is the normal wireless communication process. Now, let's look specifically at how encoding is done. Encoding is divided into source encoding and channel encoding. Source encoding is actually about converting the original signal into a digital signal, compressing it by converting text into a digital signal, then encoding it. What is channel encoding? It's the technology for error correction and detection to enhance the success rate of channel transmission Everyone needs to be clear about this. Channel coding enables maximum recovery of information on the receiving device, reducing the error rate. For example, many signals are sent to the destination, right? How does it distinguish each signal's origin? So, we perform this channel encoding to ensure channel transmission. But to effectively transmit text, we have to add a lot of mechanisms. That is, channel coding brings a burden, so the transmission efficiency is reduced. This is what we call encoding technology. What is modulation and demodulation? First, our digital signal is like this. Modulation is converting the digital signal into a wave. Ordinary sine waves carry no information. But if you want to transmit information, you have to make some changes. This is where modulation technology comes in. It is divided into 3 different methods. The first is amplitude modulation, for example. Originally it's A, which is a 0 signal. When I want to express a 1, it changes to 2A, then it's decoded, and similarly decoded in the following process. This is amplitude modulation. What is frequency modulation? Very simple. It's normally at a certain frequency. When I need to change, I slow down the frequency or increase the frequency. Originally, one period of time could only transmit 1 wave. Now it transmits 2 waves. Here, a piece of information is conveyed. So by adjusting the frequency, the purpose of transmitting the signal is achieved. This is frequency modulation. The last one is phase modulation. What is phase modulation? At different points, the phase might be different. Maybe here it's the normal phase. When modulating, I make a 180-degree adjustment. This way, you can also convert the information you want to transmit. We use these 3 modulation methods to transmit the signal to the counterpart. If the counterpart receives the information, it needs to decode the frequency signal into a digital signal. Decode it into a form like 0101, then the digital signal is decoded into the original data. This is what we call modulation and demodulation technology, using changes in 3 different parameters to transmit our data.